we implement the bisection method using Python. So this is the Python script. I already read it, and I'm going to explain the details. Here, I just created a file called bisection.py. As we mentioned before, .py means it's an extension for Python script. So here in this Python bisection.py file, I'm going to first import several important packages that are often used in numerical analysis. So we can import this numpy package. It's numerical package in Python, and I'm going to make a shortcut as np. So later on, I can just call the function inside as np dot the function I want. Now I can also import the math package to do some basic math calculations. And now the major part is to define this bisection method. So this method has several inputs. We said we need to give the function f, which you want to find the root for. And you need to give the two endpoints, a and b. You need to tell when it's going to stop. So this is the stopping criterion or error tolerance that you want your algorithm to stop. This is the maximum number of iterations. Okay. If you want to connect two words, just use underscore. So I put an explanation for this file. It's always a good practice to make comments or like explanations for the code you are writing. Here you have a triple quote. So everything in between this will be considered as comment. It will not be executed, but it will be helpful for you to or for other people to read what this algorithm is about. Then, as we said, that this is trying to use the bisection method to find the root of f in the interval ab, and that the algorithm is going to be terminated when the distance between your or the size of your interval is smaller than E tolerance, the tolerance you set, or the maximum number of iterations you reached. Okay. So in this first part, I just do a quite trivial thing, just in case that someone use your code, but they put A and B swapped, means the A is even bigger than B, then yeah, in that case, you just switch A and B. Okay, so here this temp, you just temporarily record the value of B, and then you assign A, the value of A to B, and then you assign the original value of B to A. So it's just a switch the two. Okay, now we do some basic initializations. We set the iteration counter to 0, and then we set f of A and set f of A and f of B as these two values. It's just evaluate the function f at these 2 points A and B. Now we need to consider several things. If these two values have the same sign, so they're both non-zero, but they have the same sign, in that case it just means that their product is greater than 0, right? That means they're either both positive or both negative. So in this case, you know that the bisection method is not going to work. So we should just terminate the algorithm. But if you terminate it, you better put a error message just to indicate that this what actually went wrong when you executed this algorithm. So we can print this this sentence just to say that, okay, if A and B, f of A and f of B have the same sign, then this method doesn't work, and you can just output a not a number value, just indicate that P is nothing, okay, because the method doesn't work. And then if this is not the case, then we may also encounter the case that f of A is already 0. So that means if you evaluate f at point A, you already got a value 0. That means A is already a root. Right? In this case, you don't need to do anything, just output the value A, because that's already a root. Okay, so here in this line, I actually output this value of P, but also indicate that how we found this point P. P is essentially just A. So this is a sentence that you can output. So you can output a sentence including several numbers. And here, because I know that when f of A is already 0, I just assign the value of A to P, and P is our root. So the f of P, so here I need to actually see what is the value of P when I print it out. So I need to use this percentage %g. This just means that it's going to output a number, and what exact number is this p here. It should be p, because here this is another number and it's going to be p as well. Also here is p. Okay, so in this case, it's just going to print the value, just to say the f of p, whatever the value is, and it's set to 0, so the endpoint p is actually a 0 of f. It's a root of f. Similarly, for this case, if f of b is already equal to 0, then you just assign the value of b to p and output a similar sentence. Okay, so now if neither of this happens, you're just going to know that f of a and f of b are both non-zero and they have different signs. So this is where the bisection method can actually start working. Right? In this case, we can initialize the initial iteration counter to 1 and then start the main loop. So the main loop is just like the algorithm, the pseudo algorithm we introduced in class, where we're going to run this loop. Here, this loop, we're going to just check as long as the iteration number has not reached the maximum iteration number you set, we will find the middle point p between a and b. So it's just right between the in the middle between a and b. So this is just half of a plus b, and then we're going to evaluate the function at the point p. So now we got a new point p and its function value. Then we're going to check if this point p as the function has a value 0 at the point p, that means we already found this root, right? This p is actually the root we want. That's one case. The other case is that the distance between a and b is really, really small. So here, this np.abs means the absolute value between absolute value of b minus a. If it's smaller than preset error tolerance, then you're going to stop this loop. So here, you're going to break this loop, basically break this while loop. It will jump. It will not continue to run whatever left. You just jump out of this while loop. Okay, so that's this what this stands for. So if this is not happening, so if p is not the root, or the b and a are still far away, then we know that we can choose p to be either a, or we're going to set a or b to p, right? Because we need to halve the interval. So in which case, we're going to choose b as a p. So if f of p and f of b have the same sign, that means f of p will have a different sign than f of a. So in this case, we're going to just set our new b to be p. So we're going to choose, so if f of p and f of b have the same sign, that means the f of a and f of p will have a different signs. In this case, we'll just reset our interval ab to ap. Okay. Otherwise, if f of p and f of b have different signs, if their product is negative, then we know that we can just choose pb as our new interval, or just choose the right half. Okay, so if this is happening, we choose b to be p. Otherwise, we choose a to be p. Okay, and then after all this, we can increase the iteration counter by 1. So this will finish the while loop here. And then if before we output the value of p and iteration number, we want to give an error message or kind of a warning message, just in case that we actually run the maximum number of iterations, and it's just a stop because it has reached the maximum number of iterations we set at the beginning. So in this case, your iteration number or iteration counter is bigger than, or it doesn't have to be bigger than, just equal to will be enough. But just for simplicity, to set it to be greater than or equal to maximum iteration number we set, then we just output some error or warning message here to say that, okay, this is not, the solution P is not that reliable because we were running this algorithm for too long. It just stopped because of this maximum number of iteration was reached. Okay, so after all this, we can output the value of p. You can also output the actual number of iterations you run, and then this finish the main algorithm here. So now you can see that only this part is the essential part, right? This for loop is actually the essential part of the algorithm. But for your code to run more reliably, to encounter different kind of situations, you need to include all those cases, so that your algorithm actually can do as many or as much as possible when different things happens. So that's basically what the main code is. Now let's try to try it on the problem exercise problems. So for example, the problem 2.1.4, so that's the fourth problem in the sections 2.1. So there we're given a function f that is, actually can look at it here. So f of x is x to the fourth minus 2 times x cubic and minus 4 times x squared plus 4 times x plus 4. Okay, so that's actually the function. So we're going to define this function in this way. So this x4, I'm just repeating these things. So for every given value x is going to return this value right here. Okay, just given to return this value here. Now we're going to try to apply the bisection method to this f over different intervals. So before that, we're going to set our tolerance to be e to -2. You can set it to be e to -3 or even smaller. I think this is what is required by the question, so I just use this one right here. And I'm going to just artificially send a maximum number of iterations to 100. And then I'm going to try the first interval in the question. It says that the A and B should be -2 and -1. So I'm going to apply the code we just wrote. Remember, this is the code we wrote, and it requires this many inputs. Okay, I write it particularly in this way. It's just that I can copy this sentence to all the later different intervals. I just need to change the interval right here. So I don't have to write like here. I don't have to write it like -2, -1, and later on I forgot what that is. Okay, but here then it's pretty clear. We're just going to apply the bisection method to this f over this interval AB, where A and B are given like this. Okay, and the tolerance and the maximum number are already given here. And then after you have done the calculation, then you need to ask the Python to output or to print something on the terminal, or give you some like a sentence or a statement about what kind of root, what value of the root he found, and what is the interval they used, and how many iterations it took, right? So you can print this sentence. Says I found a root. This is the number, right? And in the interval, again, I'm going to put A and B here in this many iterations. So f is the real number, so you already have a digits. The d means it's an integer, because the iteration counter has to be an integer. Okay? That's why that's the 4 numbers I need to put in these 4 locations in order, which are p, that's the root we found, and b are the given 2 endpoints of the interval, and the iter will be the number of iterations we actually used to find this p right here. Okay, so that is the first interval in the question. The other interval is just the same, right? We just copy this code down and just change the endpoints. So for the second part, it's 0 to 1, 0 to 2, and this is 2 to 3, and -1 to 0. Okay, so that's the this is this part. Okay, so now, sorry, I should put it here. So this is the 2.1.4, and you can expect that it's going to output the root for these 4 different intervals. Now let's move on to the next. We're going to do this 2.1.6b part. So the function is given like this. is 2, you can read here, 2x, 3 times cosine of x, e to the x. So in Python, you need to write it as 2 times x, 3 times math dot cosine. I think you can use NP as well. It doesn't. I think both of them have this cosine function and the exponential function of x. So for every given x, the function f is just going to return the value here. Then you can print it out just to indicate that what is the function you're actually solving for. I'm going to write this f of x. And then we're going to set tolerance. I think it's e to the -5 as required in the question. And again, I'm going to set the maximum iteration number to 100. You can set to some other number you want. But this will be my choice. And then you can run this for interval a and b. I think the question gave a interval 0, 1. But if you use 0 and 1, you actually cannot find any root because the function actually takes the same sign as these two values. Okay, so I think this is typo in the book. If we choose 0 and 2, we actually can find the root because the root is actually 1.2 something. Okay, so that's the problem 2.1.6b, or the problem 6b part in section 2.1. Okay, so now we have everything. We can try to see what is going on with this. Okay, so we're going to, so here, this is my computer, and I actually saved this file under this download folder. So I'm going to just copy this to my server. So you don't have to do this. If you already have the Python installed, you can just click run here and you get the result. But I'm just going to be a little bit fancy since I have the Python installed on the server. I'm going to just copy this file called bisection.py to the folder, sorry, to the local server I have. Also to this folder. I'm just going to send the file there. And then I'm going to, so here this is my server, and it's already, the file is already copied here. So I'm going to just run Python 3 bisection.py. Okay, and then I just press enter, and I'm going to output the results. So now you can see it output this part. This is the first 2.1.4. So f is this, as we printed out. And in the 4 cases, it indicates what is the root found in what interval within how many iterations. Okay, so you can directly output this in the answer. Okay, so for example, here we output a root this in the interval -1, -2 to -1 in 8 iterations. That's actually correspond to this part. The interval is -2 to -1. Okay. So similarly, we're going to look at this. This is the problem 2.1.6b. Here the function is given like this. So if I set the interval to be 0, 1, you actually can see that, or f of a and f of b will have the same sign. So bisection method can now output a value. That's the error message we put in the case here, just in case that this happens. So we're going to output this error message. So you will not find a root. You find the root NA, it means not a number. Okay. But if we increase the size of the interval from 0, 1 to 0, 2, then it can actually find a root like this within 19 iterations. Okay, so that's the output of this script.